All right, let's have a look at how we differentiate these trig functions. And going to start off, we've got to define some limits in order to do this, because I'm going to end up using first principles. Now, if you think of your sine curve, the limit as x approaches 0, that's nice and easy. It's going towards the origin, so that would be 0. Cos x would be 1, it's approaching 1. Tan x would be 0 as well. So all we've got to do is think of a graph, we know what those limits are. Now, that's, by the way, a circle. We introduced that the other day. Okay. Drawing in a sector here. And you might be thinking, what on earth has this got to do with trig? But you shall see. The angle at the centre I'm calling x. I'm giving it a radius of 1. Now, what I do know is the area of that sector will be greater than the area of that triangle, AOC. I'm going to create another triangle by drawing in a tangent and then extending the other radius through. So we get a right angle triangle, of course, because radius is perpendicular to the tangent. And it's fair enough to say that the area of the sector is less than the area of that right angle triangle. Okay. Well, we have different formulae, whatever, to work out each of those areas. So for the small triangle, half AB sine C, area of the sector, half r squared theta, and half base times height for our right angle triangle. And we have this expression here. We notice a half we can get rid of. So I now know that x, so the size of the angle, will always be in between the sine of the angle and the tan of the angle. The angle's got to be in radians, remember, because we're using our half r squared theta formula where the angle had to be in radians. So when we're talking about radians, the angle at the centre will always be between the sine of the angle and the tan of the angle. I'm going to divide through everything by sine x. Now, sine x on sine x, of course, will just be 1. Tan x on sine x will be 1 on cos x. And then, of course, the middle bit, which I'm actually interested in, is the x on sine x. If I now look at the limit of this as x approaches 0, well, we said that cos x approaches 1. So my right-hand expression, 1 on cos x, must approach 1. So as x approaches 0, this expression x on sine x must be in between 1 and 1. Thus, we've now found its limit. So the limits as x approaches 0 of x on sine x will always be 1. Now, this is a very important limit. You actually do get questions in the extension paper just simply finding limits of expressions like this. Yeah? Yeah, because the reciprocal, of course, would still be 1. So, yeah, it doesn't matter whether it's sine x on x or x on sine x, that limit will be 1. So we might get a question like this. As x approaches 0 of 5x on sine 5x. Well, it's still going to be 1. As long as the algebraic term is the same as the angle on the other side of the fraction, it's always going to be 1. So 5x on sine 5x, because I could easily, if x is approaching 0, I could easily say, well, 5x is approaching 0, and then it satisfies our limit. So that is just 1. Something like this, however, x on sine 3x, well, again, we've got to match the algebra with the angle. So I need to make that x 3x. But I've got to balance it out. I can't just change the question. So it'll be a third times 3x on sine 3x. But we know the limit as x approaches 0 of 3x on sine 3x will be 1. So the whole limit in this one would be 1/3. So make the... Don't change the angle, because you can't factorise outside a trig. It's always the algebraic bit on the other side of the fraction. Make that match the angle. All right, let's now see how we differentiate sine x. And I'm going to use first principles. So function x plus h minus function x all over h as, whoops, that should be h approaches 0 there. I've just done a cut and paste and didn't change my x to an h. So expanding out, sine, remember sine, cos, cos, sine. If it's the sine, it's the sine. Minus sine x all over h. I've got to try and come up with an expression for this. So I'm going to rewrite it slightly. Now, I've found every term that has cos x, which is just the 1, and I get cos x outside of sine h on h. And I know the limit of sine h on h, so that bit's okay. What I'm left with, if I factorise the sine x out, I get cos h minus 1 on h. And at this stage, I don't know that limit, so we've got to try and work out that one. Okay, so I'm going to change this one here. Cos h, I'm going to use my double angles, is 2 cos squared h on 2 minus 1. Right? I'm using the idea that cos 2 theta is 2 cos squared theta minus 1. But then there's another minus 1 there, and so that's why it's become minus 2. Right. Now, 2 cos squared minus 2 is sine squared, or 2 sine squared. So I've now changed my 2 cos squared minus 2 to be 2 sine squared h on 2. Okay, so that's where we're at, 2 sine squared h on 2. But I've now made it over h on 2. Well, hang on. Remember, the top was 2 sine squared. Well, I've moved that to the bottom of the fraction. In other words, I've divided both the top and the bottom of the fraction by 2. So the bottom now becomes h on 2. And the angle matches it. The only problem is it's sine squared. Our limit is not for sine squared, but our limit is for simply sine. So I rewrite that and say, well, that is sine h on 2 on h on 2 times sine h on 2. Now we can find the limits. Because if I sub into the sine h on h, that limit's 1. If I sub into the sine h on 2 on h on 2, that limit is 1. If I sub into the sine of h on 2, that limit is 0. So I've got 1 times 0, which is 0. That's why I need to break it up. See, when it was sine squared, very tempting to say it's 1, because the limit of sine x on x was 1. But sine squared is not. Its limit is actually 0. So I'm simply left with cos x times 1, sine x times 0. Well, it's just cosine of x. So differentiate sine x, we get cosine x. To generalize that, if we have the sine of any function, we differentiate the angle. That goes out the front, and we change the sine to cosine. So it becomes the derivative times the cosine of function x. Okay, let's now try and find cos x. Well, now that I know sine x, finding cos x is a little bit easier, because rather than going back to first principles, I can change cosine x to be the sine of 90 minus x, or pi on 2, because I need to use radians in this case. Right? Complementary ratios. Remember, sine and cosine? Sine is 90 minus x. Now I can differentiate, because I know how to differentiate the sine function. Differentiate the angle, well, pi on 2 is just a constant. Differentiate minus x, I get minus 1. So, and the sine goes to cosine. So I get minus the cosine of pi on 2 minus x. Cosine pi on 2 minus x can be tidied up. That is, of course, you don't all have to rush me with that answer there. It's sine x, complementary ratios again. So there's the interesting one. Differentiate sine, you get cosine, but differentiate cosine, you get minus sine. So to generalize that one, if you have a cosine of some function, differentiate the angle, but it'll be minus sine. So we get minus the derivative times the sine of function x. Well, let's have a look at tan x then. And again, I'm not going to go back to first principles, because I now know how to differentiate sine x and cos x, and we can rewrite tan as sine over cos. And I'll use the quotient rule. So, square the bottom becomes cos squared x. Write down the bottom, cos x. Diff the top, sine x differentiates to cos x. Minus, write down the top, sine x Diff the bottom, differentiate cos x, we get minus sine x. Look what happens, we get something very lovely. On the top, we have cos squared plus sine squared, which is right. And then on the bottom, we just have cos squared x. 1 on cos squared, well, the reciprocal of cos is sec squared. And there's our answer. So differentiate tan, it goes to sec squared. Generalize that one. If we have tan of function x, differentiate the angle, put it out the front, the tan changes to sec squared, the function x. So let's look at some examples. We have the sine of x cubed. Differentiate the angle, 3x squared, sine changes to cosine. Notice the angle never changes. The angle is always the same function. The tan of 1 over x. So differentiate the angle. Well, 1 over x, the derivative of that is minus 1 on x squared. The tan changes to sec squared. The angle doesn't change. So I've got minus 1 on x squared, sec squared, 1 on x. The log of cos x. So I'm differentiating a log function, which says, okay, do the derivative over the function. The function is cos x. The derivative of cos x is minus sine x. So derivative over function becomes minus sine x on cos x, but sine x on cos x is... So the derivative of the log of cos x is minus tan x. Tan x all to the power of 5. Remember, with trig, we don't use parentheses. We put the power next to the actual trig ratio itself. So this is tan x all to the power of 5. So it's the chain rule we have to use. Bring down the power, the 5. Lower the power, it's now tan to the power of 4. Diff the inside. So tan x is the function that's inside the parentheses, although we haven't got parentheses there. Differentiate tan x. You get sec squared x. So we have 5 tan to the power of 4x times sec squared x. The swimming one. Swimming carnivals in a couple of days. Appropriate example there. Cosy x. Okay, so it's a cosine function we're differentiating. We've got to differentiate the angle. The angle in this case is e to the power of x. Differentiate e to the power of x, we get e to the power of x. Well, it's the easiest derivative. So e to the x goes out the front. Cosine changes to minus sine, and the angle doesn't change. So we have minus e to the x, sine e to the x. There we go. Well, we've got a good day's work ahead of us.